Hello everyone. My name is Haruto Takita from University of Tokyo. Today, I'd like to talk about, do we still need human instructors? Investigating automated methods for motor skill learning in virtual co-embodiment. Let me show you the outline. This study investigated the efficiency of motor skill learning using virtual co-embodiment in which instructor and learner share a virtual avatar. Previously, co-embodied with a human instructor, we proposed to co-embodied with an AI that learns the motion of the human instructor. I'll start with the background of this study. Many daily activities involve the learning and use of various motor skills. When learning motor skills, we observe the instructor's movements from a third-person perspective, while we practice from a first-person perspective, which makes motor learning inefficient. In this context, virtual co-embodiment is gaining attention as a method for motor skill learning. Virtual co-embodiment is the system in which a virtual avatar is controlled based on weighted average of two users. In this figure, the person on the left is responsible for wrist movements, the person on the right for arm movements, and the weighted average of the two users is reflected in the center virtual avatar. It has attracted attention as an efficient motor learning technique, because learners can observe the instructor's movements from first-person perspective. In previous research, it was discovered that virtual co-embodiment enhanced the efficiency and the retention of learning skills. Specifically, we can clearly see these effects in tasks that involve motor automation and those that rely on memory. However, there are several challenges in motor skill learning using virtual co-embodiment. In particular, instructors need to be proficient in VR, teaching motor skills, as well as in using virtual co-embodiment. Additionally, one instructor is required for each learner, making it difficult for this learning method to become widely adopted in society. To solve these problems, we proposed a method to learn motor skills co-embodied with machine-learned AI learning motion data of human instruction. This allows AI to be in charge of instructors who have previously been human, thereby aiming to enhance motor learning without the need for human instructor. Next, let me explain the details of the AI model. Long short-term memory was used as the AI model. LSTM is a type of recurrent neural network that is often used to predict motion data because of its ability to consider long-term time series. For the input, we used the past 50 frames of learner's hand position, velocity, target position, and so on. An LSTM layer with 64 neurons was used as the middle layer of the model. One frame of instructor's hand position were output. Thus, learner's hand position in the last 50 frames is input and next instructor's hand position is output. The training data consists of motion data collected during dual task performance while co-embodied with a human instructor. For training, we used leave one out cross-validation, where motion data from 21 participants were used. These figures shows the output when training and test data are input to the model. The plot points represent the learner's input data, the correct data from the human instructor, and the output data inferred by the AI instructor. As these figures show, the AI instructor model, shown in green plot, can generate behaviors that closely resemble those of human instructor, shown in orange plot. In summary, we developed an AI model that outputs the instructor's motion when the learner's motion is input. The learner then practiced the motor task co-embodied with the motion data generated by the model. We adopted a dual task, where participants simultaneously drew a 5-pointed star with left hand and a 7-pointed star with right hand. When they touched the correct sphere, its color changed to red, allowing them to proceed to the next target position. Performance was evaluated based on the number of correct vertex touches within 30 seconds. The experiment consisted of 4 conditions: co-AI, co-human, co-record, and alone with 84 participants. In the co-AI condition, participants practiced co-embodied with AI instructor. In the co-human condition, participants practiced in real-time co-embodied with human instructor. In the co-record condition, participants practiced co-embodied with human instructor recorded data. In the alone condition, participants practiced alone without co-embodiment. Next, we explain the procedure. First, participants performed the task alone once to measure the baseline. Then, they practiced the task 10 times, either co-embodied with instructor or alone, depending on the experimental condition. Finally, as a test, participants performed the task alone 3 times. As measurements, we defined improvement as the score of each trial minus the baseline score. Here, we explain the hypotheses of this study. To evaluate motor learning efficiency, we compared co-embodiment with an AI instructor to solo practice and co-embodiment with a human instructor. We hypothesized that motor learning efficiency in the co-AI condition would be higher than in the alone condition, and that motor learning efficiency in the co-AI and co-human conditions would be similar. Now, I will explain the results. This graph shows improvement on the vertical axis and the number of trials on the horizontal axis. On the horizontal axis, the section labeled 1 to 10 on the left side of the dotted line represents the practice trials, while the section labeled 11 to 13 on the right side represents the test trials. As indicated in the legend at the top left, the red line represents the co-AI condition, where participants were fused with an AI instructor. The blue line represents the co-human condition, where participants were fused with a human instructor. The orange line represents the co-record condition, where participants were fused with recorded motion data from a human instructor. The green line represents the alone condition, where participants practiced alone. Looking at the practice trials, the co-human condition showed the highest improvement, followed by the co-AI condition, and then the alone condition. Therefore, hypothesis 1, which states that motor learning efficiency in the co-AI condition is higher than in the alone condition, was supported. These results indicate that practicing while co-embodied with an AI instructor improves performance more than practicing alone. However, it does not enhance performance as much as co-embodiment with a human instructor. Additionally, looking at improvement in the test trials, the co-AI condition showed significantly higher improvement than the alone condition, with no significant difference between the co-AI and co-human conditions. Therefore, hypothesis 2, which states that motor learning efficiency in the co-AI and co-human conditions is similar, was also supported. These results indicate that co-embodiment with the AI instructor developed in this study can achieve the same level of motor learning efficiency as co-embodiment with a human instructor. Next, we will discuss the difference in improvement between the practice and test trials. In solo trials, performance declined after co-embodiment with a human instructor, whereas it was maintained after co-embodiment with an AI instructor. This result suggests that while the human instructor may have provided excessive support, the AI instructor likely adapted its guidance to the learner's proficiency level. Finally, I will discuss future work. As shown in this table, the human instructor greatly improved performance during practice but led to lower scores when testing alone. On the other hand, the AI instructor did not enhance practice performance as much as the human instructor, but it helped maintain performance in solo testing. Since there is a trade-off between improving performance during practice and maintaining performance in solo task execution, as shown in this table, it is important to develop an AI model that can adjust the level of instructional support. Such a model should maximize performance during practice while minimizing performance decline in test trials. Additionally, further validation is needed using more general motor tasks beyond the dual task approach employed in this study. Here is a summary of this presentation. A co-embodiment system that enhances motor learning by observing teacher movements from a third-person perspective has the challenge of requiring a skilled instructor for one-on-one training. To address this, we developed an AI trained on human instructor movement data. By co-embodying with AI-generated movements, we aim to improve motor learning without a human instructor. We conducted an experiment comparing our proposed method, which co-embodiments with AI instructor, to the traditional method that co-embodiments with a human instructor, using a dual-task motor exercise. The results showed that practicing with the AI instructor achieved the same learning efficiency improvement as practicing with a human instructor. Thank you so much for your attention.